For the air scan though, so I'm going to set that up, and again, while that's measuring, we can keep chatting. All right, so let's go back here. 20. So I just want to double check. So we're going to do the other one that they recommend for fun.
So what additional information, for example, let's say I'm doing a semiconductor measurement, like silicon, you look at the transitions, like electron
Sure.
transition.
Yeah, yeah. Where it occurs. Yep.
Yeah. So would a simple uh, this kind of an equipment not give me that kind of information?
Um,
Like I
Possible. Well, again, a reflective scan can give you also where those absorptions are, but we're also gonna be very surface sensitive too. When you're what's your oxide, what you're growing on top of it, things like
right.
that. I mean, there's other ways to get similar information. Sure, I'm just kind of giving an example where you might want to have a finer resolution. Yeah, or what's your composition? If you have silicon germanium or something
Mhm.
like that, right? So I think most everything's the same. The only thing I'm going to change is now my angle in this case. I'm going to shim it back. I think it'll clear because of that slot, but I don't want to. I want to make sure I'm fully clearing it, so I'm just going to put this little shim here. So basically, that pushes the stage back out of the way when when I'm doing the air measurement. Everything else is the same. I just need to set the angle to 90. I think they do. Oh, except they want to do a fixed polarizer here. That's the only difference. Since air theoretically air should have psi of 45 degrees. So tangent of psi is RP over RS. Tangent of 45 is 1
Mhm.
because if you're going through air, it's not PNS is not changing. So RP equals RS at air. So we keep the polarizer fixed for that particular measurement. Everything else I think is the same. Just wanted to double check that before we do this. You might see that every once in a while since it was happening. It said closing monochromatic slits.
Mhm.
So since we were just sitting here chatting for a little bit, it's gonna if it's been a couple minutes, it's gonna close them down so it's not exposing the sample. Maybe you have something there you don't want to expose, or just shining light. It doesn't have to. So it'll close down the slits every once in a while, so it's not shining light. So we're gonna do acquire data, spectroscopic scan. I'm actually gonna delete I'm gonna delete this for the second because or delete my generated data so I don't have that on the background. One thing I did show, so since I kind of closed this hardware window earlier, I'm gonna delete the generated data. If I want to get it back, okay, like oh crap, where did my hardware window go? Or this window got really weird or whatever. Two things. You can either go up. These two are global. So again, if I click on any window here, these menu items will follow what I click on. Similarly, you can right click and get these menu items where I right click. Okay, but these always stay. So your units, those types of things. But this window one, like say, where's the hardware window? I can reopen it, or this reset window layout can be handy because it kind of just brings back everything kind of to like a default. Okay, so that can be useful. So we're going to acquire data, spectroscopic scan. So the things I'm going to change, I'm going to do 90 to 90. Um, and the only other thing I care about is I'm going to do a fixed polarizer in this case at 45. It's
What are
got
we doing the air scan again?
just for so I can see how the quality of the air looks like because its initial setup. If air doesn't look like air, then I've got other problems.
Oh,
Just to make sure the tool. I mean, the MSE on the cowl wafer look great, but this is kind of our what can I check? I can check the cowl wafer and I can check air. The air is my only true known. Air should be. Again, if you have a sample, I'm dependent on the thickness and
yeah,
other things too.
yeah.
So, so that's the other one. If so, during an install, I'm checking those two things, and then after that, it's just whatever we want to do for fun. Um, so that's the same.
Okay. So like you recommend us doing the air?
No, no, you don't. I recommend calibrating off this wafer probably
Yeah.
daily or at least every few days. I mean, again, you'll get used to it. It's not depends on how tight of stuff you're looking for.
Mhm.
If you ever have a concern that something is off with the instrument, this is a check.
Okay.
So you can check this wafer. That's why it says like whatever the manual calls, system checks or something. Basically, you can if you have concern on the accuracy of the tool, I can check error and I can check this wafer. Those are the kind of things we can gauge against to see like, okay, the tools looks fine or something's weird. Okay,
Mhm.
so, but especially this is the initial setup. We're gonna do that air scan. we're gonna at least measure. If hopefully I set that right. I just want to push the stage out of the way. And then stuff like what are my measurement settings? I give my suggestions for standard things, but wavelengths that you're going to end up doing and stuff that really is application dependent. You know what? You don't have. This is a wide wavelength range tool. You don't have to always measure the full range. Okay. And so again, this will probably take another 15. So the first one's always going to be a little bit off on the estimate because it was moving stuff around. So usually give it 2 or 3 points to get a better estimate on the time. And at least hopefully. Okay, it's about 20 minutes. Okay, so again, for this measurement, psi should be 45, delta should be 0. Again, across the spectrum. Okay.
We're doing what angles are we doing?
Well, currently, so there's 2 ways I could do this. I could either, I'm doing air, so I could either say 90 degrees or 0 degrees, really. If I say 0 degrees, I'd have to click the other button that says transmission measurement. In that case, it would move this to 0. That's what you do for a standard transmission scan. So I could have, the other way to trick it is just to say do 90. That way it goes 90, 180. But if I do it the way, I'm just following what the manual said.
Gotcha.
So if I do it this way, I've just got to make sure the stage is out of the way.
Yeah.
If that's at 0, I'll go through the middle. If it's at 90, most of the beam misses because of the slot, but I don't want to risk it. Yeah. So I just get it out of the way. So again, there's going to be some deviation here, right? But this is still very, very small. But we'll check this in a little bit. So we'll let that go. Again, delta should stay near 0. Psi should be near 45. Psi is always going to be a little bit easier than delta just because of the rotating analyzer. Now, if we were not using the auto retarder here, delta would be very, very noisy. Okay, because again, if you're just trying to linearly polarize light, basically delta is undefined. Again, whether it's right or left circular, and your delta itself can vary over a 360-degree range. So again, you have a phase delay between wave 1 and wave 2. Well, every full wave it repeats itself, right? So, but basically, if you don't use the auto retarder, delta is noisy at 0 and 180, and we're at 0 right now. And you don't know whether it's above or if I'm in between or the other. So what's handedness? So you only can measure from 0 to 180 rather than 0 to 360. So So that comes into play if you're looking at things on glass for sure, because delta is going to be usually close, or transparent films on glass is the most common example. But again, measurements. So right now I'm using the auto retarder. Measurements will be faster without it, or your reflectance measurements actually will be faster too, because we just need to see what's the raw intensity, right? But it's just the baselining. But this case, I definitely need to use the auto retarder because delta is at 0. Okay. So by again, I'm always in kind of, it's a research instrument. I'm doing the most I can with it versus if I was doing 20 samples a day, then what's the bare minimum I need to figure out what to get the answer I want, right?
Because I know back in Missouri we used to do a lot of those films, and I don't know if we did the auto retarder because the measurements took
What were your typical measurement times?
Very quick, and sometimes even like 5 minutes.
Okay, then you probably were not using the auto retarder. Yeah. You might have been using some of the default settings. Okay.
Maybe I was just.
And again, if that's adequate to give you the information you want, great. But you were not doing things on glass, then I assume.
No, on silicon.
On silicon, and you guys had thick enough to have interference oscillations usually. Yeah.
Usually we have a thickness range from 250 to 500 nanometers.
So again, I guess my comment there is, you will likely get almost the same answer with or without for a lot of those materials. And some of yours was anisotropic, I think, but it was uniaxial. Does that make sense?
Mm-hmm. Not ours.
No, your porous samples were not. They didn't show any anisotropy, or.
Anisotropy in terms of what?
The refractive index was different. So the in plane versus the out of plane. So basically, if this was your sample, sometimes they would exhibit uniaxial anisotropy. So the refractive index in the plane, so X and Y would look the same, but that would look different from Z.
Yeah, maybe it is.
And now you don't need a more advanced measurement for that. But again, they're sometimes having, or if you're non-uniform and stuff like that, there you kind of want the depolarization information as well. To get the depolarization, you need to have the auto retarder on. So try it both ways. I mean, obviously, if you can get away with a 5-minute measurement instead of an hour measurement, great. But if your 5-minute measurement is lacking or it's like something you're just not sensitive to it, then those more advanced settings will help.
That's manifested in the MSE or?
That's just manifested in, well, your fit quality. You know, are you describing the data features? Does your data? We can look at some of the data and see
Okay.
if I would say, well, technically, what I would probably do is I would do 2 scans. I mean, if you're gonna target a certain sample, it's gonna be very similar. Like here's samples are gonna usually look like this sample. I do a very, very detailed measurement to see what's the best you could do. And then I do the faster measurements without those settings and see, can I get the same result if I do this and this?
Yeah.
And if I can't, then is the difference well within what you're looking for, or that's a problem? Okay. But if you're really doing 5-10 minute scans, and you're probably doing several wavelengths, I'm pretty sure that means probably no auto retarder, because it takes about 20-30 seconds per wavelength with the auto retarder. Okay. But I'm also doing 100 revs here too, so that's a lot of averaging time compared to the default. And then so essentially what's going to happen is, so this is it's a double chamber monochromator. It's got multiple gratings, so during certain spectral ranges it'll switch to the other grating to be more efficient for splitting out the light. And what else? Briefly with the reflection, so again, there's multiple ways to do that. If you're just doing a single wavelength angle scan, the whole thing about the intensity-based measurements, transmission intensity, reflection intensity, is that we need to reference it to something. So we need a baseline. And so that's where it comes into, our beam. So we can move it to white light here in a second, I guess. But the beam is several millimeters right now, okay, at least. And then on this side, there's actually an aperture that there's a little pin. I can close that iris if I want to capture some of it. But normally for ellipsometry, we're not trying to collect the full beam. We kind of throw away the edges of the beam, okay, just for some various reasons. If I'm doing a pure intensity measurement, that's not advisable, because when you do your baseline measurement, your beam might be here. You put your sample on there. If your beam moves a little bit, well, if you're not collecting that full beam, any movement of that beam during, or any drift of your lamp in between your baseline and your real measurement is a direct error. Okay, so similarly here, this is a very nice base, and it's easier to do vertical versus horizontal because you don't have to worry about gravity. But if I baseline in the air condition like I'm in right now, and then I put a sample on there and it's not perfectly aligned, and I go reflection, well, my condition for the air measurement versus reflection, that beam might have been a little bit off. So a lot of times it'll be a relative error. Everything will be shifted a little bit. Okay. And sometimes if we're trying to get the most accurate reflection, sometimes we'll actually do the baseline off the cow wafer or off a similar. You could define other wafers. I've got an apps note on it. I don't think it's in the manual. Because also what happens in reflection is that the beam inverts. It mirrors. So at normal incidence, your beam's just coming in. But if I reflect, well, that beam is going to, so the beam's, it's a mirror. So it's going to, so if there's any hot spot in the beam, whatever that, so if you're trying to reproduce the same beam before and after, sometimes it's better to baseline off of a different reference sample that you can define. Sometimes that can really kind of tune down the accuracy. But if you're just trying to look at where is this plasmonic shift happen, or where does it, then that's probably less of an issue.
I think we should do the right way.
Yeah, but again, there's things you can try, or again, try both and see if they make a difference in your case. Yeah. So basically, so this is just a software installer. Okay. These will need to be on any computer. You're running VASE. So if you go put it on your office computer, you have 2 more in here. The other one stays on that computer. Okay. So that's basically if you don't want to have to be in the clean room fitting data. Again, there's 2 fibers here. We're going to leave the red fiber on there because for the most part that covers the full range of this tool. There's a fiber, a mid-IR fiber here that if this was extended to 3 or 4 microns, we would be using. We still ship it because this one, I was telling Zach, it crosses over in transmission around 2200, 2300 nanometers-ish. This one will work out to 2500 nanometers. It's just starting to drop off quicker. So if you are like doing a lot of work above 2300 nanometers, you could consider putting this one on. Otherwise, I would just leave that one on because this one will not transmit all the way in the deep UV. So it's kind of that fiber's been a nice fiber because it covers a really wide range by itself. But the reason that you have a secondary fiber in here is for that very little end. And now we can cover with one arm out from what you have. This is the widest range we can do with one arm. If we had a secondary arm, we used to be able to go to 3200 on that secondary detector. We stopped doing that detector about a year or so ago because we were having some performance issues. We offered it for many, many years. But we do have a secondary arm that goes out to 4 microns. But that's liquid nitrogen cooled. So it's a little bit, it's if you want to use it, there's a pour, basically use liquid nitrogen to run that one. So it's possible, it's harder. We do an IR VASE. No, our IR VASE goes from 1.7 microns to 33 microns. That's a completely different tool. So and that is IR based. That's covered. So that's covering the mid IR basically for that tool. All right, so that looks good. And so you said you want to wait till tomorrow. Do you want to start a different sample now?